Dear students, in the previous class we have seen one way Anova, that is a completely randomized design, we call it as CRD. In this class we will see another technique called randomized block design. The class objectives are: estimate the variance components in experiment involving random factors. What will happen in Anova, we are considering some factors, we are saying that effect of that factor, what is the effect of that variance. But unknowingly there is a possibility that some more variable may influence our response variable. So, that unknown variables and variance due to that unknown variables, we are going to remove it, then we are going to do the analysis, then we will see what is the effect of that one. Then understand the blocking principle and how it is used to isolate the effect of nuisance factors. So, what we are doing here in randomized block design, we are going to isolate the effect of nuisance factors. Then design and conduct experiment involving randomized block design. A completely randomized design CRD is useful when the experimental units are homogeneous. If the experiment units are heterogeneous, blocking is often used to form homogeneous groups. Why we have to go for RBD, randomized block design? A problem can arise whenever differences due to extraneous factors, that is ones not considered in the experiment, cause the mean squared error term in this ratio to become large. What will happen? Due to that nuisance factor, the value of mean squared error will become very high. In such cases, f value in equation can become very small, signaling no difference among treatment means when in fact such difference exists. So, what will happen here in the MSE? There may be some error term which are due to external factors. So, we are going to find out how much error is due to external factor, that we are going to remove it, then we are going to conduct the f value. Experimental studies in business often involves experimental units that are highly heterogeneous. As a result, randomized block designs are often employed. Blocking in experimental design is similar to stratification in sample. In stratification in sampling, what we are doing, if the samples are heterogeneous, based on certain criteria, we are grouping, we are stratifying that sample, so that each strata will have homogeneous samples. Here also it is similar to stratification in sampling. Its purpose is to control some of the extraneous sources of variation by removing such variation from the MSE term, that is a mean squared error term. This design tends to provide a better estimate of the true error variance and leads to a more powerful hypothesis test in terms of the ability to detect differences among treatment means. We will take one sample example. This sample example is air traffic controller stress test. Why this air traffic controller? He has to schedule various aircraft, what time it has to be landed, what time it has to be taken off. So, he is the person who has to allocate different slots for landing and takeoff. So, this job is very stressful job. We will see one problem, this one. A study measuring the fatigue and stress of air traffic controllers resulted in a proposal for modification and redesign of controllers workstation. So, what they are planning, they are going to redesign the workstation, because this sometime the workstation may affect the stress level. If it is the workstation is very narrow, people get stressed more. Okay. After consideration of several designs for the workstation, 3 specific alternatives are selected as having the best potential for reducing controller stress. So, they have identified 3 alternatives. The key question is, to what extent do the 3 alternatives differ in terms of their effect on controller stress? So, we are going to see to what extent the different workstation design is going to affect the stress of the air traffic controller. In a completely randomized design, a random sample of controllers would be assigned to each workstation alternative. Generally we will assign. However, controllers are believed to differ substantially. It is not what we are assuming, because the sample is not homogeneous, because different controllers are affected by different level of workstation design. So, the controllers are believed to differ substantially in their ability to handle stressful situations. What is high stress to one controller might be only moderate or even low stress to another. So, what is happening here, the sample is not homogeneous. Hence, when considering the within group sources of variation, that is MSE, that is called mean squared error, we must realize that this variation includes both random error and error due to individual controller differences. In fact, managers expected controller variability to be a major contribution to the MSE term. This is a setup. So, what happened? There are 3 workstation designs. We call it system A, system B, system C. This is a controller 1. So, in controller 1, when we put into system 1, the stress level is measured in terms of 15. So, when controller 1, when he was subjected to work design 2, workstation design B, he is expecting the stress, assume that the stress is measured in terms of a kind of a questionnaire. So, the 15 is the score. So, higher the score, higher the stress. So, controller 1, controller 2, controller 3, controller 4, there are 6 controller. So, since each controllers are different, they are not homogeneous, we are going to block it. We solved this example using Anova in Python. So, we have to import pandas as PD, import numpy as NP, import scipy, import statsmodel.api as SM, from statsmodel.formula.api import OLS. What I have done, the data which is in the table which was in the previous slides, I have typed in an Excel, then I have imported. That file name is rbd.xlsx. So, that I am going to save in the name of data frame. So, when I show the output, this was system A, system B, system C. So, I am using melt command. So, data equal to pd.melt df.reset underscore index, comma id underscore wheres index value underscore wheres equal to system A, system B, system C, data dot columns in bracket index treatments value. This I also told in the previous class. This melt command is used to bring all the values in 2 columns, one column for treatment, another column for values. So, model equal to OLS, the value is the dependent variable tilde C the treatments, comma data equal to, that file name is data dot fit. So, Anova underscore table equal to sm.stats.anova underscore lm, lm is a linear model, model comma type 1. Remember this is type 1, because whenever there is a 2-way Anova, we have to use type 2. So, Anova underscore table. So, what is happening? This error sum of square is 3.2. So, what is happening? This value is more than 0.05. So, we are accepting null hypothesis. What is the meaning of accepting null hypothesis? Here, so if it is a 0.05, so it is the p value is 0.06, we are accepting null hypothesis. When I accept null hypothesis, what is the null hypothesis here? The level of stress is equal for different 3 workstation design. Suppose H naught equal to workstation, this is stress, average stress level for workstation A, workstation design A, this is B, this is C. So, H1 is mu A not equal to mu B not equal to mu C. So, at present what I am concluding, I did not block it. What I am concluding, there is no connection between workstation design and their average level of stress. Next what I am going to do? I am going to do blocking going back. So, there are 3.2s there error, actually 49 when you divide 49.15. So, this is sum of square error is 49, mean sum of square is 3.2. So, this 3.26 due to blocking effect I am going to remove or subtract certain level of variance from this. Then again I am going to conduct, let us see what is happening. So, this was the given data set. So, the treatment mean is there are 3 treatment that I am calling this system A, system B, system C. So, x dot 1 bar is 13.5, x dot 2 bar is 13, x dot 3 is 15.5. Okay. We know this is our Anova setup. Look at the previous, when is the CRD in the completely randomized design or one way Anova, there is no this column blocking. Okay. There was only treatment and error. Now we are introducing the blocking. So, what is happening? What is the degrees of freedom? Total number of element minus 1 degrees of freedom. In treatment, there are k treatment k minus 1, blocking there are b blocking b minus 1. So, how to find out this k minus 1 b minus 1 is nt minus 1 minus k minus 1 minus b minus 1. So, we will get k minus 1 and b minus 1. So, ms treatment is ss sum of square treatment divided by k minus 1, ms mean square blocking equal to SSBL. Actually, this data we will not use that one, we will use only ms treatment divided by this MSE, SSE divided by k minus 1 into b minus 1. Actually, this much portions we will remove this, we will subtract it. Okay. So, Xij is the value of the observation corresponding to the treatment j in the block I, x dot j bar is the sample mean of jth treatment, xi dot bar is sample mean of ith block, x double bar is overall sample mean. What is the step 1? First we will find out the SST, that is a total sum of square. Total sum of square is summation I equal to 1 to b, summation j equal to 1 to k, xij minus individual element minus overall mean whole square. Okay. So, in that way we are getting SST is 70. Then compute the sum of square due to treatment. So, there are 3 treatment. So, B is number of replication treatment 1, that is a 6, column 1 mean 13.5 minus overall mean 14 whole square plus, okay, 6 is common, we brought 6 everything this side. So, 13.0 comma 14 whole square plus 15.5 comma 14, so 21. The third step is compute the sum of square due to blocks. So, due to blocks is there is a k treatment. Okay. So, xi dot bar minus x double bar bar. So, there is a row wise what is the mean. So, everywhere there are 3 treatment, I brought 3 this one. So, 16 minus 14, how we got this 16, I am going back. This 16 minus 14 whole square plus 14 minus 14 whole square and so on this way. Yeah, 16 minus 14 whole square plus 14 minus 14 whole square plus 12 minus 14 whole square plus 14 minus 14 whole square plus 15 minus 14 whole square plus 13 minus 14 whole square, that is equal to 30. So, this much variance is due to blocking, this much sum of square. So, compute the sum of square due to error term. We know that from SST we have to subtract treatment sum of square minus blocking sum of square, that will give SSE. 70 minus 21 minus 30 is 19. So, this 19 is a true SSE, because this SSB amount which is due to extraneous variable, that we are noise variable. So, error due to this we are removing this while finding SSE. Now, what we are getting, yeah, the whatever value which I have given I have kept it here. So, it is a 10.5 divided by 1.9, even though we find this one we will not use for calculation. So, 5.59, so the value of p value is 0.024, if alpha equal to 5%, we have to reject our null hypothesis. So, previously what has happened, when we do without blocking we have accepted our null hypothesis. I am going back, see this, we have accepted null hypothesis without blocking. After blocking, our decision is completely changed. So, what happened? We have rejected the null hypothesis. We will do with the help of Python. Import pandas as PD, import numpy as NP, import scipy, import statsmodel.api as SM, import statmodel.formula.api, import OLS. OLS is ordinary least square method, because the regression and Anova is like two sides of the same coin. The sequence of learning regression and Anova is, first you have to learn Anova, then you have to learn regression, because there is a close relationship that I will see after this lecture is over. After 2 lectures we will go for regression analysis. I have imported, okay. There are 3 columns. Then I am using the melt command, so that I will bring all the values in 2 columns. One is for here 3 columns, because I am going to do the blocking. So, blocks, treatments and values. So, model equal to OLS value tilde C block plus C treatment. You see that now there is a blocking effect I included. Previously there is no this term C into blocking. So, data equal to data, close the bracket and fit. So, Anova underscore table equal to sm.stats.anova underscore lm, model 1 is a type 1, Anova underscore table I am getting. You see this one here, yeah, this is a 0.024. So, it is less than 0.05, I am rejecting the null hypothesis. So, what we are concluding? Finally, note that Anova table shown in the table provides an F value test for treatment effects, but not for the blocks. The reason is that experiment was designed to test a single factor workstation design. The blocking based on the individual stress differences was conducted to remove such variation from the MSE term. However, the study was not designed to test specifically for individual differences in stress. So, what is happening here is the blocking, exactly what we are doing, the error due to blocking is removed while finding the influence of workstation design on stress level. We will go for one more problem. We will use this randomized block design. We will go for one more problem. An experiment was performed to determine the effect of 4 different chemicals on strength of a fabric. These chemicals are used as a part of permanent press finishing process. 5 fabric samples were selected and a randomized complete block design was run by testing each chemical type once in a random order on each fabric sample. The data shown in the table in the next slide. We will test the difference in means using Anova with alpha equal to 1%. This was the table. What says this? Different chemical type is there, different fabric sample is there. The replication is 5, because the same after adding chemical type 1, when we conduct the fabric strength, we have conducted 5 samples. This was the row mean, this was the row average. So, what will you do? I have typed this data in an Excel, in Excel file rbd2.xlsx. So, this was the data. So, using melt command I am going to bring into the 2 variable, one is on value, that is a response variable, another on the treatment. So, this you have to type as it is, that is the purpose of this pd.melt. So, when I am running model equal to OLS, value is the dependent variable, tilde is the treatment is the independent variable, data equal to data, because this data is the way I have taken this after using melt command is the data. The file name is data, so I am using data equal to data dot fit analysis of variance underscore table equal to sm dot stats dot anova underscore lm model comma type equal to 1. So, we used a table. So, what is happening? You see that mean this is 0.4777. Here we did not do the blocking. We will do the blocking, and what is happening to here we are rejecting our null hypothesis because the probability is less than 0.01. So, we are finding SST. SS treatment is, you see this formula is so comfortable for using calculator. So, yij whole square minus y dot, this notations already I have explained what is A. A is the number of treatment, B is the number of blocks. So, this is SST is 25.69, yes, that is the total sum of square. Treatment sum of square is 18.04. SS block is y dot j whole square by a minus y double dot square dot by ab. So, this is 6.69. So, the error term, you see that how I am finding SST total sum of square minus sum of square due to blocking, that I am subtracting, minus sum of square due to treatment. So, I am getting 0.96. So, this is a true error without having blocking effect. So, what is happening, the mean square is here 0.08, right. So, we will go back, what was the mean square without blocking? Yeah, you see that without blocking it is a 0.47, now it is 0.08. The mean square error is removed because we have removed the error due to blocking. So, here the value of f also, when you can compare it, it is significantly high, 75.13, there is more chances for rejection. Previously what is the f value? I am going back, here f value is 12, 12.58, now f value is 75.43. There you are certainly, you can say that you will reject your null hypothesis. So, the ANOVA is summarized in the previous table. Since f equal to 75.13, which is greater than the table value, that is a 5.95 which you got from the table, we have done ANOVA also, that is the p value is very low. We conclude there is a significant difference in the chemical types so far as their effect of the strength is concerned. Previously we have done it traditional way, now we will use Python for doing the blocking, that is for doing the randomized block design. Import pandas as PD, import statsmodel.api as SM, from statmodels.formula.api import OLS, from statmodels.stats.anova import anova underscore LM. So, you save the file in the name of df equal to pd.read underscore excel df, this was the output. Again you see that we are using melt command. After giving the melt command, the data has become this format. So, what is happening? Fabric samples 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, see these are one group, this is another group, this is another group, this is another group. See, this is a chemical 1, that's one group, chemical 2 up to this, chemical 3, chemical 4. So, the purpose of this pd.melt command is for this purpose, that will, now there are 3 columns, one is the fabric sample. So, the value is the dependent variable, chemical type treatment is independent variable, fabric sample that is the blocking variables. Now, pass this model equal to OLS in quote value tilde C fabric, because fabric is a blocking effect plus the chemical, that is the treatment effect, data equal to data dot fit. When you run this, you are getting, see the f value is, which we got traditional in manual method, we got this one. So, you see that p value. So, what we have done, we have taken one problem, we have solved without blocking what was the status. In this problem we are rejecting, then we go for blocking, after blocking also here rejecting, but when you look at the value of f, that is significantly it is increased. So, what will happen, without blocking you may conclude on things, you may accept null hypothesis because the error term is very bigger. After blocking the error term become very less, then you may reverse the decision, we can reject the null hypothesis. That is the application of this blocking. Dear students, in this lecture what we have seen, just I am summarizing, we have seen what is randomized block design, we have seen what is the need, when will we go for randomized block design, then we have taken a problem, that problem was solved without blocking, we have seen what is the result, then the same problem with blocking, then we have seen how the result has changed. Even without blocking also we have used Python code, we saw what is the result. Then with blocking also we have used Python code, then we see what was the result. So, in this what we have done, we have taken 2 problems, for both the problems we have solved with blocking or without blocking. In the next class we are going to the another type of ANOVA, that is a two-way ANOVA. Thank you very much.